Welcome back once again to History of Mathematics. We are working through chapter 15 of Stuart Hollingdale's book, Makers of Mathematics, where we are talking about the work of Sir William Rowan Hamilton and George Boole. Now, both of these folks were 19th century Irish mathematicians, and Boole in particular is notable for his work in logic and set theory. And both of these provide important extensions of the usual algebra that we see, where the rules are derived from the rules of arithmetic. So in logic and set theory, we still have a structure where we take objects. In set theory, our objects are sets or collections, and we have rules for combining these objects into new ones. And the rules are intersection, union, and complement. And in the structure of logic, the objects are statements. And we have rules for combining statements together to make new ones. And the rules there are and, or, negation, and implication. There's another one there that doesn't quite translate as well to set theory, but it's in there. So, these new algebraic structures give us important examples for really understanding mathematics, because once we get into the 19th and 20th century, we see mathematics isn't really about computation, it's about understanding structures. So let's transfer to the document camera and look at some examples of set theory from George Boole. So George Boole created these algebraic rules for logic and set operations. And we're going to focus on the set operations. And when we're dealing with this structure, our objects are sets or collections, and these are the operations that we can do with those sets. If I have a set, I can find its complement. If I have two sets, I can take them and make the union. And a convenient visualization for these set operations is the Venn diagram here. So if I have two sets and want to talk about the union, I'll call the sets A and B. And in the Venn diagram, I have a circle representing the set A and another circle representing the set B, allowing the possibility that they do have some things in common right there in the middle. You notice in each of the Venn diagrams, I have a box that represents the universal set U, which is everything under discussion at the time. And if I want to form the union of two sets, A and B, what I do is I take everything in the set A together with everything in the set B, and I form one larger set that contains both of the two sets under discussion. If I want to take A and B and find the intersection, I would take the elements of A that are in common with the elements of B. In other words, I would look for the overlap between the two sets, and that would be represented by this region here in the Venn diagram. If I wanted to look at the complement of a set, which is denoted by this notation right here in our textbook, I would look at everything in the universal set that doesn't belong to A. Right? So the closest thing to complement in regular algebra is like negative or opposite. Okay, now if we have specific sets where we know the elements we're talking about, we can get a little more concrete and we don't have to use these Venn diagrams here. So let me give you an example there of that type of situation. Okay, so in this case, my universal set is going to be whole numbers 0 through 9. And my sets A and B are listed right here. So A is the even numbers that belong to U, and B is everything less than 4. So the first operation I want to look at is the union of the two sets. And to form the union, we take everything in the first set, everything in A, together with everything in the second set, and we form one bigger set. So notice this union has all the elements of A. It's got 0, 2, 4, 6, and 8. It's also got all the elements of B, 0, 1, 2, and 3. Notice we don't list anything twice. If 0 belongs to the set, then 0 belongs to the set. You don't need to say it again. If I want to look at the intersection of the two sets, well, I look at what the two sets have in common, and that's the intersection. So you'll notice 0 belongs to both sets, so 0 belongs to the intersection. 2, that belongs to both sets, so 2 belongs to the intersection. If I want to talk about B complement, well, I look at the set B, I compare that to the universal set. B complement would be everything in the universal set that doesn't belong to B. So there's B complement right there. Now the neat thing about set theory is it kind of has a unique interaction between the operation of complement and the operations of intersection and union. So if I take A intersect B and then do the complement, well, I've got A intersect B right here. It's just the element 0 and 2. So if I were to take the complement of A intersect B, I would look at everything in the universal set that doesn't belong to A intersect B. And that would be a heck of a lot of stuff right here. And it's something you could check for yourself, but you would get the same set if you took A complement first. So we can think about it, we can visualize it right here. A is the evens, so A complement would be the odds, 1, 3, 5, 7, 9. Okay, now notice this is bigger than just A complement. I need to take A complement together with B complement. Okay, B is over here. B complement would be 4, 5, 6, 7, 8, 9. If I were to union 1, 3, 5, 7, and 9 with 4, 5, 6, 7, 8, 9, this is the set I would get right here. Okay, so notice the complement doesn't exactly distribute over each of the parts. Notice what happened to the middle right there. It turned an intersection into a union. Okay, and it has that effect on that operation. So it gives us another kind of algebraic structure. So both the work of Hamilton and Boole give us examples of new algebraic structures that follow rules similar to the ones we know from ordinary arithmetic, but they're not quite the same. And as we transition from 19th century mathematics to 20th century mathematics, that's the big theme. We're focusing more on structures and what properties structures need to have to do the operations that we want. So the ordinary structures that we know from arithmetic, they carry over to the high school algebra that we know, and that's what we use in calculus and stuff like that. But that's not the only structure. And set theory and logic and the quaternions, they give us examples of new structures that follow some of those rules, but not all of them. Okay, Sophie's going to go explore, and we are going to continue our work through this book and finish it up. There's only 2 chapters left. The next one is about the work of Cantor and Dedekind, and they both did some significant things involving infinity, and the book finishes up with a chapter on the mathematics of Einstein. So both very interesting topics.